that you want to ask me? You guys at home want to say something? I got the chat box open, way too big. Okay, so here's some problems that relate to what we were doing. Remember that a geometric series is a series that has the form where each term is just a constant multiple of the previous term. And that multiplier is what I'm using R for, and A is the first term. We decided that a geometric series will converge if that multiplier in absolute value is smaller than 1. And it converges to the sum S is A divided by 1 minus R. So the geometric series might be disguised in some ways. Maybe like this one. To find out for sure if you've got a geometric series, you can rewrite it. You can manipulate the exponents, or you can just start expanding it. Start putting out some few terms of this thing. The counter in this example is n, and it starts with n is 1. So I'm going to write out the first 3 or 4 terms. When n is 1, I have 9 to the first power and 4 squared. Now n is 2, so I have 9 to the 0 power, which is 1, times 4 cubed. Now n is 3, and I have 9 to the negative 1 power, times 4 to the 4. And then finally, n is 4, and I have 9 to the negative 2 power, 4 to the 5. So I can kind of write that like, oh, I don't know. If I move from 9 to the first power to 9 to the 0 power to 9 to the negative 1 power to 9 to the negative 2 power, then I know one of my multipliers has to be 9 to the negative 1. I'm also changing the 4 by increasing a power of 1. So I think my multiplier in this case is 9 to the negative 1 times 4. Does everybody agree? You can always find the multiplier by taking any 2 adjacent terms and take the term on the right and divide it by the term on the left. And that'll simplify to the multiplier R. If I rewrite the 9 to the negative 1 as 9 in the denominator, then we see that that fraction is indeed smaller than 1. So this particular geometric series converges, and it converges to A, the first term is A, so I've got 9 times 4 squared over 1 minus R, R is 4/9. 1 minus 4/9 will give me 5/9. So let's simplify that by flipping that over and multiplying. So I have 9 squared times 4 squared over 5. I don't want to multiply that out, but that's going to be our our sum of this particular geometric series. These will be probably the easiest series that you encounter. Oh, maybe second easiest. We'll get the easiest one today. All right, so one of the giveaways for a geometric series is that you've got a base that's a number and the power is the counter. So a number raised to the counting variable. So I can tell you already that the next one is going to be geometric. And we'll start our counter this time at n is 0. So let's fill some of those in. -4 to the 0 power is going to be 1. And then I'll have 5 to the -1 power. So that's the same as 5. Now n is 1, and I have -4 cubed. N is 1, so I have 5 to the 0 power. So -4 cubed is going to be a -64? Now n is 2, and I have a 5 to the first power down here, and a -4 to the 6th power. So how is it that we're moving from one term to the next? What's our multiplier here? -4 cubed over 5. I agree. But -4 cubed over 5 is huge, isn't it? 4 times 4 is 16, times 4 more is 64, and it's going to be a -64 over 5. And so when I take the absolute value of that r, I get that. That's bigger than 1, so this series diverges. You keep adding terms that get bigger and bigger and bigger and bigger, so this thing's going to go to infinity. Now I want to show you a series that's not geometric, but it has some of the properties that the geometric series had, in that we were able to rearrange our terms to see whether or not it converged. Let me write out the first so many terms of this thing here. My counter this time is a k, and it starts at k is equal to 1. So when k is equal to 1, I have 4 minus 2 down here. So my first term will have a 1/2 in it, and then a 4 plus 2 gives me 1/2 minus 1/6. There's my first term. And I don't want to simplify it. Now k is 2 to get the second term. 2 times 4 is 8, minus 2 is 6. 8 plus 2 is 10, so I have 1/6 minus 1/10 as the second term. Now k is 3. 3 times 4 is 12, minus 2 is 10. And then 12 plus 2 is 14. And let's go one more. I've got room for one more term. K is 4. So 16 minus 2 gives me 14. 1 over 14 then. And then 16 plus 2 is 18. Now look closely at that sum. Let's even make it bigger for you. What do you notice about this sum? Take those parentheses off. I put them on there so that you can separate the terms. But they're really not holding anything. I'm just adding stuff together. When you take those parentheses off of there, you see that adjacent terms are the same, but opposite in sign. That this term will add to that one to give me 0. This term adds to that one to give me 0. And so on. All of my terms are going to disappear, except the first one and whatever happens at the end, because this goes on for infinity. So what I'm going to do to investigate whether or not this converges is to look at the sequence of partial sums. Our sequence of partial sums will converge if it has a limit. And we have a theorem that said if the sequence of partial sums converge, then so does the series. So we will consider Sn. That's the sum of the first n terms. So if I run this term out here and stop at term Sn, then I'll have all of this line plus, let's put the Sn term here. I'm replacing k with n. I'll have 1 over 4n minus 2 minus 1 over 4n plus 2. So Sn takes me out to here. The series itself goes on forever. That's what this says. But if I just truncate it right here and look at these, the pattern will continue all the way through here so that these inside terms will add each other out all the way down the line till I get to this nth term, and it looks like the first one should cancel. And I should be able to write Sn in closed form as 1 over 2 minus 1 over 4n plus 2. So that's describing my partial sums as a sequence. So I put it in the cute brackets. That's the nth term of my sequence. A sequence converges if it has a limit. So I'm taking the limit. So I'm going to take the limit of this last term here. Letting n go to infinity. Only the second fraction has the n in it, and it's in the denominator. So we know that term's going to go to 0, which leaves us with 1/2. So since the sequence of partial sums converge, to 1/2, so does the series. Maybe we'll just call that our partial sums test. That's going to be one of the hardest tests to use. This particular sequence that has the property that all the inside terms are the same but opposite in sign is one called a telescoping series. Just like a telescope can be stretched out and then collapsed to its smallest form, we can collapse this series down to its smallest form. I'm going to write that up here. if you happen to have a telescoping series or one that you suspect to be telescoping, then you can do this partial sums test. But they don't always blatantly look like this. What was unusual about this is that I had two separate fractions. But what if I had this written as a single fraction? Well, that's no problem. I learned back in chapter 7 that I can take a single fraction and write it as smaller fractions that added to that by doing a partial fraction decomposition. So if I suspect a telescoping series, I'll try to write it as the difference or the sum of several fractions, and then see if I can find the partial sums test. So with that warning, here's one that's put together. Maybe. Nope, it's on back. Come on, focus. There we go. So right now, the only series that we have are geometric and then hopefully telescoping. Well, this one's clearly not geometric because we said a geometric series has the counter k or n as the exponent and the base is a number. I've got it the other way here. So what I'm going to try to do is see if this is a telescoping series, not by writing out the terms from that form, but by doing the partial fraction decomposition first. So let's write that in factored form. I know factors of 2 that add to 3 would be 2 and 1. So let's start with writing 1 over k squared plus 3k plus 2 as 1 over k plus 1, k plus 2. And then let's find constants a and b, where a is above the k plus 1 and b is above the k plus 2. Do our partial fraction decomposition. So I'll race you. Let's have a race finding a and b. Isn't that fun? I'm going to multiply both sides by k plus 1, k plus 2. And I'll have a 1 up here. A times k plus 2 plus b times k plus 1. If k is equal to -1, I'll get a. So I have 1 is equal to a times -1 plus 2 is just 1. So I get a is 1. If k is -2, then I'll get b. So that drops out. I have 1 is equal to -1 times b. So b is -1. And that means that my series is equivalent to this one. K is equal to 0 to infinity. 1 over k plus 1 minus 1 over k plus 2. The minus sign in between gives you a hint that this is probably going to be telescoping. So let's run a few terms. Let's write out the nth partial sum. So I start with k is equal to 0 in this case. When k is 0, I have 1 over 1 minus 1 over 2. Now k is 1, so I have 1 over 2 minus 1 over 3. Now k is 2. Gives me 1 over 3 minus 1 over 4. So sure enough, I've got this thing telescoping. So let's stop out here when k is n. So without the little parentheses around the individual terms, the -1/2 adds to the +1/2, the -1/3 adds to the +1/3, all the way down the line to the second to the last term. And those will all add each other out like that. all the way down the line, and there's only 2 terms left. That's the closed form of Sn. If we can write the nth partial sum without the dot, 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 then all we've got to do is take the limit. The limit exists, the partial sums converge, and so the series converges. This has the n in the denominator, so that means as n goes to infinity, that fraction goes to 0. So my sequence of partial sums does converge. So by the partial sums test, our series converges. Means it adds to a finite sum, and that finite sum is, in this example, the same as what the partial sums converge to. So you've got a couple in your web work that are a little bit different. They're not just algebraic fractions. You've got a trig function, you've got a logarithm. But if you write out the first few terms, I think you'll see that you have a telescoping series. And if you can get it down to just 2, maybe 3 terms without the dot, dot, dot in it, then that's the closed form of the nth term. And if that has a limit, then the sequence of partial sums converge, and so the series converges. Now the next one, I'm not sure if I could write this as partial sums. Let's see if the denominator factors. Let's see, I'd have a 3k and a 1 and a k and a 1. To give me the 3k squared to get the plus 2k, I would need that, right? Does that give me the plus 2k in the middle? It does, right? But look at what's going on here. We can't do partial fraction decomposition because the degree on top is not smaller than the degree on the bottom. So we would have to divide first. I'm not so keen on that. Not so keen on dividing first. Remember what we said the other day, that if a series has any chance of converging, the terms way out yonder, real close to infinity, have to eventually start going to 0. Otherwise, you're adding in things that are relatively large. Since the degree on top is same as the degree on the bottom, I can see my terms are not going to 0 when k is large. What are they going to? 4/3. When k is big enough, I'm always adding 1 1/3 to my series. So there's no way that's going to converge. It's going to keep getting bigger and bigger and bigger. We're going to call that our test for divergence. A necessary condition for a series to converge is that its terms have to go to 0. It's not a sufficient condition, but it's a necessary condition. All convergent series have the property that their terms toward infinity go to 0. If the terms toward infinity do not go to 0, then we can automatically say that the series diverges. And we're going to call that our test for divergence. If the limit as k goes to infinity of the kth term, so we're testing the series, I wrote it in terms of k. If that limit is something other than 0, then the series diverges. That doesn't say that if the limit is 0, that the series converges. Oops. If the limit is 0, we don't know jack. Because there are divergent series whose terms go to 0, and there are convergent series whose terms go to 0. The converse, though, is true. If the series converges, its terms go to 0. But if the terms go to 0, doesn't mean the series converges. It's not a biconditional. So in this example, our kth term goes to 4/3 because the power on top is the same as the power on the bottom. So this series diverges. So my suggestion to you, almost every time you attack a problem in this chapter, is eyeball it real quick. Does the limit go to 0? If the limit goes to 0, continue. Find a test to see if it converges or not. But if the limit doesn't go to 0, you're done. You say that bad boy diverges, and you go on to the next one. So always check quickly if your series is going to have a limit to 0. If it's too much work, then maybe you're not good at taking limits, no. But it's a nice, easy way out. Okay. All right, so the next one I want to talk about is something called the integral test. So let me back up from the examples and go through the integral test with you. And this is in section 8.3. Now I said we can depict a series by a scatter plot of points. This is my counter n out here, and goes from 1, 2, 3, 4, and then it goes on forever like that. So, and these are the terms. So suppose I've got a positive term series, and maybe my terms do something like this. But as I move down the line, they form a decreasing sequence. Now I'm going to draw vertical lines connecting those, because our series is the sum of those vertical lines. If the sum of those vertical lines is a finite number, the series converges. If the sum of those vertical lines is an infinite number, the series diverges. Now those y values can be used to construct rectangular boxes of base width 1. So let me connect these over like this. And hopefully when I do that, it reminds you of a Riemann sum. And a Riemann sum generates a definite integral. If we can find a positive function that passes through these points, like that, and we integrate that function if that particular function has a definite integral from, say, 1 to infinity. If that integral converges, then that means that the area under that curve is finite. And the area under that curve can be approximated with those rectangles if I were allowed to make the base width shrink. If the integral converges, then we're going to say that the series converges. Why not? It's going to lie essentially under this curve, give or take a few pieces that are sticking out, because we're going to have a decreasing set of points. So if the integral converges, then so does the series. If, however, too many of these boxes stick out toward the end, then this definite integral is going to diverge, and then so does the series. If the integral from 1 to infinity of f of x diverges, then so does the series. But we have to require that f is a continuous function that's positive and decreasing. So the formal statement of this integrals test is something like this. With a positive term series, let f be a function that passes through all of the a's. If f is continuous and decreasing, then the series does whatever the integral does. If the integral converges, then the series converges. If the integral diverges, then the series diverges. So we just have to make sure we have something that we can integrate as this improper integral. Come on, not a good book. Finding that function is easy. We just have to make sure the function is decreasing before we apply this test. It doesn't work just willy-nilly. We've got to make sure that we have a decreasing continuous function. Now in the picture I've drawn you here, I've got a function that isn't strictly decreasing. I've drawn a function that rises a little bit and then decreases after a while. We don't need our function to decrease over the set of all real numbers. We just need it to be a decreasing function for values of x big enough. So if we go out to here, some value out here, we only need it decreasing for x bigger than that number out there. It's okay if it does a little wiggling at the beginning, but we need it to decrease and bound that function. So here's what it's saying. If you've got a function that's on top of all of your terms in your positive sequence, and that function bounds finite area, then those guys must add up to a finite sum. But if your function is infinite, then there's too many of those bars sticking up above it, and the series is going to diverge as well. So if the integral diverges, the series follows along. And we can integrate the heck out of just about anything. Just about. So let's go back to my example. I said use the integral test to determine if the series from k is equal to 1 to infinity 1 over 3k plus 5 converges. You think, well, I got to find a function that fits that. Well, that's easy enough. Take the k out, put an x in, there's your function. So let's let f of x be 1 over 3x plus 5. And that's continuous on the counting numbers from 1 to infinity. The only discontinuity occurs at, what, -5/3? And that's not in the realm from 1 to infinity. So I know f is continuous. It's decreasing because it behaves like the graph of 1 over x. You know, that's a hyperbola that's decreasing. I just got the 3 and the 5 on there. So that keeps it in the same shape. So it's continuous and decreasing, continuous positive and decreasing. So it fits all of the things that I need in order to use the integral test. Let's just integrate it. Our lower bound is always the same as the lower bound on the counter. So I'm going to integrate from 1 to infinity of 1 over 3x plus 5 dx. And we do that with a limit. Say as n goes to infinity, from 1 to n, 1 over 3x plus 5. That's just a 1 over u du integral, isn't it? Where u is equal to 3x plus 5, du is 3 times dx. So we're integrating 1/3 1 over u du. That's a logarithm. I get, in this example, 1/3 times the natural log of 3x plus 5. Be evaluated from n is equal, from x is 1 to x is n. That bar too flat. Get down that bar. There we go. Why didn't I do that a long time ago? So I got 1/3 natural log of 3n plus 5 minus 1/3 natural log of 8. What's your verdict on this limit here? As n goes to infinity, I've got the natural log of 3n plus 5. Diverge, diverge? Diverges. The logarithm's a growing function. So as n goes to infinity, the natural log of n goes to infinity. So this becomes infinitely large right here. Taking away the natural log of 8 is not going to do much good, but this integral diverges. That means the series diverges. Series does what the integral does. Okay. Questions, anybody? F of x has to have a limit of 0 as x goes to infinity. It has to decrease. So yes, if f of x fits the shape of the curve, then it does have to go to 0 as x goes to infinity. It does, absolutely. All right, let me swap pages on you. Now the next one is the series from k is equal to 1 to infinity, k times e to the negative k squared. Now, if I just had e to the negative k squared, then I could possibly have a geometric series. Because remember, when the counter is a k, then it's possibly geometric. K squared's probably a problem. So this one's not going to be a geometric. It does have a term that goes to 0, right? If I write that as k divided by e to the k squared, do you agree that that term does go to 0? Think about our tower of power. E to a power grows much faster than just k. E to the x grows faster than x. So it does go to 0. So if we were to do the test for divergence, we know nothing. It is a positive term series. E is a positive number. K is a positive number from 1 to infinity. So I've got a positive term series. That means I just need to consider this function. F of x is equal to k e to the negative k squared. I got to figure out if that's decreasing or not. By itself, e to the negative k squared is decreasing pretty darn fast, right? Because e to the negative x is a decreasing function. And I meant to use an x and not a k. So I have the feeling that it's decreasing. I can actually show that it's decreasing by using my calculus 1. We showed functions were decreasing in Cal 1 by showing that the first derivative was negative. So let's do that just for practice. So is f decreasing? Let's look at f prime. Do product rule. F prime of x is the first times the derivative of the second. The derivative of e to a power is itself times the derivative of the power. And then the other way, the second times the derivative of the first, and the first term is just x. So its derivative is going to be 1. I'm going to factor from that the e to the negative x squared out. And then I'm going to have a minus 2x squared plus 1. E to the negative x squared is never 0, but negative 2x squared plus 1 is 0. When x squared is a half, or x is the square root of a half. I didn't consider the negatives because I'm only in the positive real number line. So if I look at the sign of the first derivative, beyond that, I don't care what happens over here. We only are interested in what happens in the long run. So I'm going to plug a number in bigger than 1 over the square root of 2, like for instance 1. And I'll have negative 2 times 1 squared plus 1 is going to be negative. So that shows that my function is decreasing for all values bigger than 1 over root 2. I have a continuous function that's decreasing. Now all I got to do is integrate it and see if the improper integral exists. So we're going to integrate from 1 to infinity, x e to the negative x squared. How are you going to integrate that one? Take u to be the exponent, and then du is part of the term here. Take u to be negative x squared. Du is minus 2x dx, so negative 1/2 du is the x dx. That's this x dx. And so we're integrating negative 1/2 integral e to the u du, and that's going to give us negative 1/2 e to the negative x squared, because integral of e to the u is e to the u. Then we evaluate this, say, from 1 to n, and take the limit as n goes to infinity. And so the limit that we're evaluating minus a minus gives me plus 1/2 e to the negative 1. E to the negative n squared is the same thing as 1 over e to the positive n squared. So that's like 1 over e to the infinity, which is really big. 1 over infinity goes to 0. So this term goes to 0. And then this integral converges to 1 over 2e. So the integral converges, and that implies that the series converges. So I'm often asked, well, the integral converged to 1 over 2e. Does that mean that the series converges to 1 over 2e? And the answer is no. It might converge to something close to that, since I drew those boxes in there. But some of those boxes will hang out of the curve, some will hang underneath it. So it'll be a close approximation to what the integral converges to, but it's not the exact value of what the integral converges to. Okay? But the fact that the integral converges is enough to say that the series converges. I just don't know to what. So let's plan on using the integral test when we see something that does have a limit to 0 and that looks like something we know how to integrate. I don't want to do the integral test on something that's a geometric series. That's no fun. But a lot of things that I know how to integrate are on this page here. Things with e's and logarithms typically are things that I'm going to integrate. The next one, though, 2 over k squared plus 9 does go to 0. So I try my test for divergence and I get no information. Limit to 0 means I know nothing. But if I take the function f of x is equal to 2 over x squared plus 9, then I know that f is positive, continuous, and decreasing. I don't have to do the first derivative because I know exactly what this graph looks like. It looks a lot like the graph of 2 over x squared, which is again a hyperbola. That 9 just moves it over a little bit. So it is a decreasing function. That means if I integrate it and get the integral to converge, then the series converges. If I integrate it and the integral diverges, then the series diverges. So I'm integrating this time from 0 to infinity. 2 divided by x squared plus 9 dx. The 2 is a constant. I can pull it out. Do you recognize the integral of 1 over x squared plus 9? That's an arctangent. This one would give me 1 over 3 times the arctangent of x over 3. So here's the 2. Then my 1 over 3 is going to give me a 2/3. Then the arctangent of x over 3. And I'm going to go ahead and get a little sloppy. I'm going to go from 0 to infinity. I won't write it as a limit. We'll just get sloppy here. So I need to know what happens here. I'm going to put it in quotes to remind you that I am just getting sloppy. Take infinity and divide it by 3, and it's still infinity, so I'm just going to put the infinity here. It's the behavior of the arctangent toward infinity. And go to 1, pi over 2. It has that asymptote up there at pi over 2. So this becomes 2/3 times pi over 2. I know what the arctangent of 0 is, do you? Arctangent of 0 is the angle that we take the tangent of to get 0. 0. Arctangent of 0 is 0. So my integral converges to 2/3 times pi halves, or pi thirds. And that implies that the series converges. But again, not necessarily to pi thirds. Any questions? Okay. This next one is going to have a name once we do it. I'll give it a name. But right now we're just going to assume that we're going to do this by the integral test. So I have to first ask you, does the kth term go to 0? If I were to take the limit as k goes to infinity of the natural log of k divided by k squared, doing our little test for divergence. Taking the limit as k goes to infinity of the natural log of k over k squared. Which grows faster, the natural log of k or k squared? K squared does. The natural log of k in our tower of power was way at the bottom. Natural log of k grows even slower than the square root of k. So the top grows slower than the bottom, which means this limit is, this limit has a value of 0. It's bottom heavy. You did L'Hopital's rule just once, you'll get the limit to be 0. In our test for divergence, if the limit is 0, we know nothing about convergence of the series. Just, we know that we have to try something. And so it's not geometric, so I can't try that. It's not telescoping because there are no minus signs anywhere. There aren't any terms that add each other out. So the only other test that we have to this point is the integral test. So we're going to try to integrate the function f of x is the natural log of x over x squared. We got to make sure it's a decreasing function. So again, I'm going to use the first derivative to show that it's decreasing. I know it's positive for k is 1 to infinity. Let's show it's decreasing. Let's take the derivative. The derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. I'll simplify that a little bit as x minus 2x natural log of x over x to the fourth. There's an x everywhere. Let's cancel one. Put a 1 there, cancel that to a 3. And so I have f prime of x is 1 minus 2 natural log of x over x cubed. There's a critical number where the derivative is equal to 0, and that's where the 1 minus 2 times natural log of x is 0. That's where the natural log of x is a half. Solve that for x by changing it to exponential form. The square root of e is our critical number. That's a pretty small number. I don't care what happens before the square root of e. I want to know what happens beyond it. So let's put the square root of e here. And let's look at the sign of f prime out here. I don't care back here. But I do want to know if this is decreasing for large enough values of x. E is 2.7-ish, so the square root of e is not quite e, right? Square root of e is going to be smaller than e. So if I use e as my test point, I put an e right here. The natural log of e is 1. 1 minus 2 is negative. The denominator is positive, e cubed is positive, so the sign of the derivative is negative, which means, yep, I do have a decreasing function. All I got to do now is integrate it. The series does what the integral does. Positive, continuous, decreasing function. Now let's integrate it. Grab another piece of paper here. The integral. So we're going to integrate from 1 to infinity our natural log of x over x squared. And I'm going to rewrite that as x to the negative 2 times the natural log of x dx. Now I need your help. How do you integrate x squared times the natural log of x? UDV. When you have a logarithm and a polynomial term, you integrate by parts. And in integration by parts, we've got to take u to be the natural log of x and dv to be everything else. So that du is 1 over x, and v is the integral of that. Add 1 to the power and divide by the new power, and you get minus x to the minus 1. And so we're going to have u v minus the integral of v du. So I'll have minus x to the minus 1, natural log of x, minus the integral of v, which is minus x to the minus 1, and then du is 1 over x dx. I left that pretty sloppy. Let's clean it up. Let's write this as minus the natural log of x over x. Let's put these two minus signs together and give me a plus. X to the negative 1 is a 1 over x. So I have a 1 over x squared or an x to the negative 2 to integrate. Well, we just integrated x to the negative 2. We got minus x to the minus 1. Now we have to evaluate this. Let's do it from 1 to n, and then we're going to take the limit as n goes to infinity. When n is in there, I have minus the natural log of n over n minus 1 over n. Now I'm putting a 1 in there, minus the natural log of 1 over 1 minus 1 over 1. Then we're going to take the limit as n goes to infinity. Make a jump back to the far parentheses. Natural log of 1 is 0. So this is 0 minus 1. That minus gives me a plus 1 out there at the end. This behaves like infinity over infinity, but that's no problem. If you did L'Hopital's rule once, you get 1 over n over 1. So as n goes to infinity, natural log of n over n goes to 0, right? Again, it's bottom heavy. Log of n grows slower than n. So this limit is 0. This is bottom heavy. 1 over infinity goes to 0. So all that stuff in the parentheses goes to 0. I got that the integral converges. So I make my grand statement, the integral converges. So the series converges as well. The integral converges, so the series converges. Okay, next one, I gave you a short and cute one. I want you to do the integral test. My series looks like 1 over k raised to the 3/2 power. 1 over k raised to the 3/2 power. That's something real easy to integrate. It behaves like 1 over x to the 3/2. A 3/2 power is a square root. K is from 1 to infinity, so those are all going to be positive numbers. 1 over the square root of x cubed behaves like 1 over x. It's also a hyperbola, so it's decreasing. Continuous, decreasing, positive. That means just integrate 1 over x to the 3/2 from 1 to infinity. If the integral converges, so does the series. Does your integral converge or diverge? It does converge. Let's quickly integrate that together. Write that as x to the negative 3/2. Add 1 to the power to give you an x to the negative 1/2. Divide by negative 1/2 puts me a negative 2 out here from 1 to infinity. So I'm going to rewrite that as negative 2 over the square root of x from 1 to infinity. So I have negative 2 over, say, the square root of infinity. Minus minus gives me plus 2 over the square root of 1. This term's going to go to 0, and so the integral converges to 2. So our conclusion is that the integral converges, which implies the series converges. This particular series has a name. It's called a p-series. 1 over k to the power of p is a p-series. And the size of p is going to tell us immediately if this thing converges or diverges. In this example 7, p was 3/2. My question is, for what value of p will the series 1 over k to the p converge? So let's think about the steps that we did in the integral test. We're integrating 1 over x to the p from 1 to infinity. And we integrate that by writing that as x to the minus p. You integrate that by adding 1 to the power and dividing by the new power. So you get x to the minus p plus 1 over minus p plus 1 from 1 to infinity. So let's retrace our steps in the previous example. That puts us to about right here. And in order to evaluate this limit, we needed this exponent to be a negative number, which put that term in the denominator. If this exponent's not a negative number, then I would have an infinity in the numerator. So what we need for this expression to converge is that this term here falls in the denominator. We would need the power to be a negative number so that I could rewrite that x in the denominator. So if I solve this for p, I would have that minus p is smaller than minus 1, or that p itself is bigger than positive 1. For any value of p bigger than 1, 1 over k to the p will converge. So let's write that out. The p-series, summation from k is equal to 1 to infinity of 1 over k to the p, will converge for p strictly bigger than 1. And it will diverge for p less than or equal to 1. The p-series where k is equal to 1 has a name. It's called a harmonic series. That was the series 1 plus a half plus a third plus a fourth plus a fifth and so on. It diverges. Do the integral test on it. Integral of 1 over x dx from 1 to infinity is the natural log of the absolute value of x. So we'll have the natural log of infinity minus the natural log of 1. but this term here is infinitely large. So it diverges. We need to train ourselves to recognize p-series. Then we just look at the size of the power. If the power is a number strictly bigger than 1, then the series is going to converge. If it's smaller than 1, then it's going to diverge. This series back here, with the logarithm in the numerator, is not quite a p-series. If I just had the 1 over k squared, that would be a convergent p-series. The series that has a logarithm in the numerator and a p-series term in the denominator is going to be called a q-log series. Here. The series 1 over k to the p is a p-series, and it converges for p strictly bigger than 1. Put a logarithm up there, and let's change the power to a q. It's called a q-log series. Let's go back and look at the integration by parts steps that we did. In our integration by parts steps on that problem, here my q is a 2, and I integrated, where did I integrate that? I integrated that here by parts. And so if you put a q here, we would write that as a q to the negative 2. And then your dv would be your q minus 1 divided by the q minus 1. All the way down to here, what we would need is that term that was in the denominator end up in the denominator in our antiderivative. So is it believable to you that we need the same restrictions on the q that we do on the p for the q-log series to converge? We need to be able to drop this x down in the denominator, so we're going to need this power to be negative. The q-log series behaves like a p-series in that it converges when that q is bigger than 1. If you don't believe me, just do the integration by parts. It takes a while. That's why if we can make that observation, then we can just look at the size of that power. All right, so let's look at a few. There to there to there. I'll give you a few here.
I have a question.
Now all these series begin from k is equal to 1 to infinity. My question to you is, for each of these, decide, do they converge or diverge? One over the square root of k, 1 over k times the square root of k, 1 over k to the negative 4/3. And so my question is, for all of these, converge or diverge? Let's start with 1 over the square root of k. Is that p-series? Square root is a power. What's the power? 1/2. So we can eyeball the size of that. 1/2 is smaller than 1, so this series diverges. Next one, k times the square root of k. So I can think of that as k to the first power times a k to the 1/2 power. When you multiply like bases, you add the exponent. So 1 plus 1/2 will give me k to the 3/2 power. My power is 3/2. My power is bigger than 1, and so it converges. The third one is not written as a p-series yet. The p-series has 1 over k to a power, but that's easy enough to fix since my exponent is negative. I can rewrite that as 1 over k to the 4/3, and now I can see my power p is 4/3. By gosh, that's bigger than 1, so it converges. Okay. P-series are easy. P-series are easy. Geometric series are easy. Telescoping, medium. Things that I have to integrate could eventually become a pain in the old rumpus if you have to integrate by parts. So what if we have something that's not a p-series? That's not something we can integrate. That is not a geometric series. Doesn't telescope. We got to do something else. Well, thank God there's more in chapter 8, because there's more something else's to do. In section 8.4, you're going to get 2 comparison tests. Right? If it looks like a duck and quacks like a duck, then it's probably going to be a duck, or at least behave like a duck. If I have a series that looks like a p-series, but it's not quite a p-series, then if it compares in the right way, it will behave like the p-series. If I have something that's almost a geometric series, if it behaves like the geometric series, then it'll converge whenever the geometric series does. So those are my comparison tests, essentially. So I need more paper. You guys making it? Good. What about you guys at home? Anything going on there? Sitting there in your pajamas taking a calculus class?
I threw on a hoodie for you in case my camera comes on.
It would converge because Q is greater than 1, correct. Well, the series diverge when Q is less than 1. It will diverge when Q is less than or equal to 1. So Q series diverges the same places where the P series diverges. P or Q is less than or equal to 1. Converges when P or Q is greater than 1, strictly greater than. Okay, let's talk about our 2 comparison tests. And some paper here. Section 8.4. There are 2 comparison tests. because one comparison test just isn't good enough. It's always nice to have two of them. One comparison test is going to be called the direct comparison test, and the other one is going to be the limit comparison test. Both of them are used for series that contain positive terms only. Everything up to this point outside of geometric series and telescoping series, all the terms had to be positive. So we're adding one positive number after another, after another, after another. So because we're adding a bunch of positive numbers, we need the kth term to go to 0 before we commence any tests. If it doesn't, then we stop and say that series diverges. If it's not a p-series, not a geometric series, not telescoping, or not something that we can integrate, then maybe we can compare to other series that is of the such. So I'm going to call all the terms that we're dealing with the A's, and I like using a K as my subscript. Let the series AK, whether K starts at 1 or 0, doesn't matter, but we have an infinite series, be a series of positive terms. So it looks like this, right? There's a point. There's the first term. There's the second term. Maybe the third one gets taller, but eventually they have to get smaller and smaller and smaller. There's my picture of the AKs. They do get smaller. Now suppose it looks a lot like a known series. I'm going to call them the CKs. Suppose what I draw in red, and I'm going to draw it just a little bit next to it. So in red, I'm going to denote that series like CKs. So suppose CK is a convergent series. With the property that all of the AKs are smaller than the CKs. It's a look-alike series. It looks a lot like the series that we're testing, the AKs, but we know it's a convergent series because probably it's a geometric series or a p-series or something like that. Does it make sense to you that if the sum of all of those little red sticks is a finite number, then doesn't make all the sum of the little pencil drawn sticks a finite number if the CKs are all bigger than the AKs? If our series is smaller than a convergent series, then the first statement in the direct comparison test says that our series will converge. So this is the first observation. Suppose CK is a convergent series where all the AKs are smaller than the CKs, then the AKs converge. On the other hand, case number 2, put my AKs again as pencil drawn sticks. There's my AKs. Now let's draw my CKs to be smaller than those. So I'm going to draw them in blue. And I'm going to call these the DKs because they're going to diverge. So suppose that DK forms a divergent series with all of the AKs taller than the decays. So if all those blue sticks add up to an infinite number, then certainly the AKs, which are represented by taller sticks, will add up to an infinite number. That's the direct comparison test. It's easy enough to remember. Just say smaller than convergent is convergent. Bigger than divergent is divergent. Smaller than convergent is convergent, bigger than divergent is divergent. If your series behave in either of those two ways, then you're using the direct comparison test. Here's an example. Take the series 1/3 raised to the k, and then in the denominator, let's also add a 2 to that. And we want to test this for convergence. Well, I threw that 2 in there. Had I not thrown the 2 in there, I had a geometric series. 1/3 to the k is a geometric series. But 1/3 to the k plus 2 is not quite geometric. Okay? So I'm going to compare it to a geometric series. Here I've got my AKs to be the given series. My terms in my BK series is just going to be 1/3 to the k. Oh, you goober. And so if I wrote that as the series symbol out here, I have that this BK is a geometric series. I've got a number raised to the kth power. 1/3 to the k is the same as 1/3 to the k, because 1 to any power is 1. Right? K starts at 1. It looks like 1/3 plus a 9 plus 1/27 plus 1/81, blah, 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 blah. The geometric series where my multiplier R is 1/3. What do you remember about geometric series with a number like 1/3 being the multiplier? Do those kind of things converge or diverge? Converges. A geometric series converges if the multiplier in absolute value is smaller than 1. So my BKs converge. Now what I want to know is my given series going to be smaller than my convergent series? So let's check. Let's check the size. Well, this is easy to compare. 3k plus 2 is bigger than 3 to the k because it's 2 more. It's a goofy looking plus sign. Let's take it away and put a better one. So if I flip my inequality by flipping both sides, remember if you flip the expression, it does indeed flip the inequality. And so 1 over 3k plus 2 is smaller than 1 over 3k. The series that I'm testing has terms that are smaller than the terms in a convergent series. And by the direct comparison test, smaller than convergent is convergent. Okay. Okay, we're going to denote the direct comparison test just as DCT, the direct comparison test. One of the series that we tested with an integral test looked something like this. So here's my next example. One over 2k minus 1 as a series is something that you can easily integrate. Right, a k to the first power. And when you integrate this, you get a logarithm. So you're going to get some constant times the natural log of 2x minus 1. We're going to let x go to infinity. The logarithm is going to go to infinity. So we can show with the integral test that this is going to diverge. But we can also compare it. I can compare it to a p-series. Just throw that minus 1 away. Right? When k is large, that minus 1 doesn't do diddly for us. So throw it away and form the comparison series to be the series of just 1 over 2 to the k. Or 2 times k. The 1 over 2 is a constant. If I want it, I can factor it out. So it's the same as saying 1/2 times the series 1 over k. That's a p-series. If p is equal to 1. P-series converged only if p was strictly larger than 1. The p-series where p is equal to 1 was that harmonic series that diverges. It diverges. So my lookalike series is a divergent p-series. If the series that I'm testing is bigger than it, then the series that I'm testing will also diverge. So let's compare sizes. Just look at the denominator. 2k minus 1 is going to be a smaller number than 2 times k. It's 1 fewer. So now flip both sides. 1 over 2k minus 1 flips the inequality. So the terms in the series that we are testing are bigger than the terms in a divergent series. And the direct comparison test tells me that bigger than divergent is divergent. So that's the direct comparison test. Both results. Smaller than convergent is convergent, bigger than divergent is divergent. Now what happens if I change this to a 2k plus 1? What if the series that I'm testing is 1 over 2k plus 1? Well, dang, it should behave a lot like the series 1 over k, right? Moving it over with minus 1 or plus 1, it still should diverge, but it's not going to compare in size the way I need it to. I could compare it to 1 over 2 to the k, but now it's not going to be bigger than divergent. So I can't use the direct comparison test. It's not bigger than divergent. My old fall through, if the sizes don't compare in the right way, is to use something called the limit comparison test. Okay, so if we were to test the series 1 over 2k plus 1, we would still compare it to 1 over 2 to the k, but the terms are no longer larger than the terms of this divergent series. So we cannot use the direct comparison test. Here to save the day is the limit comparison test. You're going to take your given series, you're going to compare it to a lookalike series. Just throw away the insignificant terms to make the lookalike series. But the lookalike series is one that you know whether or not it converges or diverges. Then you're going to take the limit of the series that you're testing to the series that is the lookalike series. If you get a positive finite limit, then both series do the same thing. They follow each other. If this one converges, so will this one. If this one diverges, so will this one. So given the series that you're testing, form a lookalike series just throw away the insignificant terms. Constants you can throw away, keep only the highest powers on the k maybe, or the terms that seem to have the biggest command over the growth of the series when k is large. Okay. You know what your lookalike series does. You compute the limit of the given series over the bk's. And if this limit, as k goes to infinity, is a positive finite number L, Lisa, L is a finite number then both series do the same. And if you think about it, it kind of makes sense. If you get a positive number of your AKs over your BKs and your BKs converge, that means that they behave a lot alike. They both steady out toward that same ratio. But if your BKs are divergent, that means that sum becomes infinite. Then so do the AKs. So that it behaves kind of like infinity over infinity, an indeterminate form that'll give you a finite ratio. So we can skip that whole comparing size business. You can just form the lookalike series, take that limit, which we're hopefully pretty good at by now, and then do what's the limit comparison test. So we'll abbreviate that one, LCT. So let's quickly test the series 1 over 2k plus 1. So in our example, the series 1 over 2k plus 1 looks a lot like the series 1 over 2k, which we know as a divergent p-series. P is equal to 1, the power on the k. Now let's not worry about size. These are the AKs. These are the BKs. We take the limit as k goes to infinity of the AKs divided by the BKs. So I have the limit as k goes to infinity of 1 over 2k plus 1 divided by 1 over 2 times k. Come on, you stupid thing. I'm dividing one fraction by another, so I'm going to flip it over and multiply. I can rewrite that expression there as 2k divided by 2k plus 1. And we're taking the limit of a polynomial over a polynomial, where the degree on top is exactly the same as the degree on the bottom. That limit can be done with L'Hopital's rule or by looking at the ratio of the coefficients. The ratio of the coefficients is 2 over 2. So my limit is just going to be 1. I got a positive finite limit. Both series do the same. My lookalike series was a divergent p-series, so the testing series is also divergent. Some folks like the limit comparison test so much better than the direct comparison test because limits are pretty easy to take. So a lot of us will just skip the direct comparison test because you have to worry about the size, how they compare to each other. Limit comparison could be bigger or smaller, who cares? But they're there. There's some problems with the limit comparison test. What if the limit we get is not positive? Like, what if we get 0? What if it's infinite? Yeesh. Sometimes getting a limit of 0 is good. Sometimes getting a limit of infinity is good. There are some conclusions we can draw on that. And so next time I'm going to give you the 0 infinity cases of the limit comparison test. But between now and next time would be next week, right? I'm going to need you to practice using these tests. The test for divergence. Do you have a geometric series, a p-series or a telescoping series, where you can just make an observation of whether they converge or diverge? Is it something you can integrate? Or does it compare, either directly or with a limit, to a known series? Got to get really good at those, because we're going to add some more fast and furiously. Okay? All right. Thank you, everybody, for showing up online and in class. Have a marvelous weekend. I'll put some more web work problems up here for you next time. Questions, anybody? If not, I'll cut you off. I have a few web work questions from assignment 9. All right, if anybody wants to see web work questions, I'm going to do some. If you don't, you can go. Cat wants 13, 14, and 15 from assignment 9. All right, let me call up web work. 13, 14, and 15. Anybody that doesn't want to see those can go. If you want to see them, on here. All right, web work, web work, web work, web work.
Can you hear me?
What you have? Assignment 9. And 15, 14, 15. Okay. Given AK to be that. All right, we want to talk about the series and the sequence. Okay, so I can put that up here. AK, peek at it again. One plus 2 over K to the K. So it said we're looking at two different things. We're looking at this guy. And we're looking at this one. This is a sequence. This is a series. It's so much easier to determine if a sequence converges. There's only one thing we need to do to check if a sequence converges. A sequence converges if it has a limit. There's buku things we can do to test a series for convergence. We had at least 5 of them, those things today. Is it geometric? Is it a p-series? Is it telescoping? Can we integrate it? Can we compare it? Or can we run the test for divergence? Right now, that's what we have in our arsenal. So I'm going to test the sequence first. The sequence converges if it has a limit. I'm going to take the limit as k goes to infinity of my kth term. And as k goes to infinity, 2 over k is going to go to 0. And this exponent is going to go to infinity. So this behaves like 1 to the infinity. That's an indeterminate form that we can't use L'Hopital's rule for, but we can manipulate it so that we can use L'Hopital's rule. This is an exponential indeterminate form. We're going to use a logarithm. Let's call that limit L, and let's take the natural log of both sides. And I'm going to slip the logarithm here and here. So we're going to have the limit as k goes to infinity of the natural log of 1 plus 2 over k to the k. And over here, I'm going to have the natural log of my limit. We chose a logarithm because one of the properties of logarithms is the log of something to a power can be rewritten as that power times the log of the base. So we're going to put that limit right here. Pull the power down, so it gives me a k right here. And now I try to take this limit. As I take this limit, this k right here goes to infinity. So does that one, which makes 2 over k to go to 0. So the second term behaves like the natural log of 1. The natural log of 1 is 0. So we get 0 times infinity. That's another indeterminate form. We're trying to get it to the form of either 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. So if you can kind of remember back in the good old days in Calculus 1, the way we did this is we took this polynomial term and we agreed that multiplying by k is the same as dividing by 1 over k. So I'm going to keep this on top. And I'm going to write this k as a 1 over k. Just an algebraic manipulation, but now as k goes to infinity, both of these guys go to 0 and the log of 1 is 0. And so I have it in the appropriate form for L'Hopital's rule. L'Hopital's rule says take the derivative of the top, divide it by the derivative of the bottom. If that has a limit, then that's the limit of the original expression. So here goes L'Hopital's rule. Take the derivative of the top. It's a logarithm. The derivative of the log of u is 1 over u times u prime. So I'm going to write 1 over 1 plus 2 over k. And now we're going in those parentheses and we're going to take the derivative of 1 plus 2 over k. Derivative of 1 is 0. Think of 2 over k as 2 times k to the negative 1. And so its derivative is a negative 2k to the negative 2. That's the derivative of the top. Go downstairs and take the derivative of 1 over k by doing the same thing. Treat it as k to the negative 1. And we'll have a negative k to the negative 2. I have the same term on the bottom that I have on the top, so I can cancel. I can cancel the minus and the k to the minus 2, and it just leaves me this 2 right here. That cancels with everything else. And so this looks like the limit as k goes to infinity of positive 2. I'm going to slide it over this. Those canceled. And then over here I have the natural log of L. Okay, so the numerator stays at 2. 2 over k goes to 0. The limit of 2 over 1 plus 2 over k is just 2. That's the natural log of L. which means L is E squared. So our conclusion is that the sequence converges to E squared. Now, it's not true that if the sequence converges, the series converges. What we needed for a series is that the terms way out far tend to 0. If they don't, then my sum is going to keep getting bigger. This says that when k is big enough, I'm adding terms of the order of E squared, almost equal to 9. I'm always adding a 9 to my series. Since the limit of the kth term of my series is not 0 by the test for divergence, the series diverges. So let me see if I can put it on here. Since the 1 plus 2 over k to the k is not 0, since that limit by the test for divergence, the series diverges. The only way a series could possibly converge is if for the limit to be 0. It doesn't have to converge if the limit is 0, but I know for a fact that if the limit is not 0, the series diverges. So it's always nice to do the test for divergence first.
Can you hear me?
You turn your microphone on, Kat. Louise, you can hear you.
Yeah, can you
That make
hear me?
sense?
Can you hear me?
Still can't hear you. Gotta chat with me, I guess. Says that is wrong because it wants to know if it's, read web work, it says if it diverges, does it diverge to infinity or to minus infinity? Well, I'm always adding E squared, so the sum is getting bigger and bigger and bigger. So you have to type in infinity. The sum becomes infinitely large. Let's look. Let me go back to it. Let me screen share. Okay. So if it's convergent, enter the series. If it's divergent, enter infinity. If it diverges to infinity, minus infinity, or divergent otherwise. So you've got infinity. But this limit's not 1. Remember, this was E squared. Now we're checking. Uh-oh. Maybe we've done it backwards. Let me see which way you did it. Oh, we got it backwards. The sequence went to E squared. This one goes to E squared. The sequence we did first. The sum becomes infinite.
Oh, okay.
Now I can hear you. What did you do differently? I jumped out of my skin when I heard you that time. Does that make sense? It's always quicker to test the sequence first. And then if you get a limit that's not 0, then you can just make this statement on your series. I bet that happens with the next problem. No, this one's different. Well, let's try it. Let's do the sequence first. Take the limit as k goes to infinity. Let me see if I can annotate. For this one, take the limit. Ooh. Oh, that's too hard to draw. 5. Dang, that's hard to draw. Not liking that. I'm gonna go back to my little pad. Got my share. All right, so for the other one. Back to here. Can you see that now? Same thing here. For web work.
Can't see it. Ah,
What's the matter?
I can't see it.
Let's see it. Let me fix that. Now?
Uh.
No. No. Okay, let me go back. What is it that you see?
Just you.
Just me. That's terrible. You don't see the little hover cam anymore.
No, not anymore.
Oh, crud. Okay. How do I fix that? Well, let's go back to Zoom. Let me do that. Okay, let's just go back to this thing here. There's screen. All right, so let's go back with this. We're back here and you're going to take the limit. We're doing the sequence here. I'm going to try to write with this game plan again. Maybe I'll type it. Give me the limit. As k goes to infinity, 5 divided by the square root of k, which I'm going to write as k to the 1/2. So what's happening to these terms as k becomes infinitely large?
It's gonna go to 0.
Go to 0. So that's our answer here. The sequence converges to 0. Okay? Now, if the kth term goes to 0, the test for divergence tells us nothing. So let's look at this series of 5 divided by k to the 1/2. That's P series.
It is.
1 over k to a power, with p equal to 1/2. So go back and look. Do P series converge when P is that size?
It diverges.
Diverge. So we get to decide, is it going to diverge to plus infinity or minus infinity? Well, these are all positive numbers. So you're always adding positive numbers. That means our sum gets infinitely large. So it's going to be infinity. Okay? So if the limit is 0, we got to do one of our tests. If the limit's not 0, then we have a test for divergence. So. All right, let's look at the next one.
This one should probably be pretty quick.
Ah, okay. Let's do the test for divergence first. Because the test for divergence is if the limit is not 0, the series diverges. So
Okay.
we're looking here, let me clear this. Here. Okay, so the limit we're doing is k is going to infinity. So we're doing the test for divergence. Since this is in the denominator and this is a constant, as k goes to infinity, this goes to 0. We know nothing. So let's look at the second one. Number 2 has a power of k squared on top, and this is the square root of k cubed on the bottom. So that's like k to the 3/2 power. So you've got a k squared over a k to the 3/2 power. Which number is bigger?
The top.
Top. If the top is bigger, then the limit is not 0, right? The limit's going to be infinite. So number 2 diverges by the test for divergence. Okay, let's try the next one. The highest power on top and the bottom is k to the 5th. So what's the limit as k goes to infinity?
1.
Or a -1, but it's not 0. If the limit is not 0, the series diverges. So that one diverges.
Okay.
Here, I can't tell which one's bigger. We probably need a calculator. Is there a calculator handy where I can see how big square root of 5 is in comparison to 2.236?
Square root of 5 is 2.236. So it's like the same. It's literally the same.
But is it bigger or smaller? Is there a digit after the 6?
Okay, I guess bigger.
Bigger. Slightly bigger, but any bigger is bigger, which means it's bigger on top than it is on the bottom. So there's no way that limit's 0. So again, by the
Divergence.
divergence, it diverges. Okay, now in here, natural log k over k minus 3, as k goes to infinity, I have k to the first power with k to the first power. So this is going to go to 1, but the natural log of 1 is 0. So I don't know anything about that. Right? I don't know that one just yet.
Okay.
Because log of 1 is 0, limit being 0, no nothing. So we skip over that one. An inverse cotangent. Oh gosh. An inverse cotangent is an animal that's very similar to an inverse tangent. Cotangent itself is cosine over sine. And so it had vertical asymptotes where the sine was 0. And that's at 0 and pi. The cotangent takes the vertical asymptotes and makes them horizontal asymptotes. So the inverse cotangent is some function that's bounded between 0 and pi. And as k gets large, it's going to approach that upper horizontal line at pi. So in other words, the inverse cotangent of k as k goes to infinity goes to pi, which is not 0.
Which is not 0.
So by the test for divergence, this one diverges as well.
Okay.
Okay, now this one has next number 7, a 5th degree on bottom, 4th degree on top. That does have a limit of 0, so we don't know anything about that one. So we stop on that. We don't know anything about that one just yet. And here we probably have to do some work. Because this behaves like, if I'm letting k go to infinity, this behaves like the square root of infinity minus infinity. And infinity minus infinity is an indeterminate form. So that one we got to do some stuff to. I don't think I can draw with this blinking mouse. Why can't I? What happens if I stop sharing that? How do I get it back to the screen? How do I get it back to my stupid? You can't see that, huh?
Mm-mm.
Son of a bitch. Yep. Who is this thing?
Is it on?
On? Turn it off. Ooh, that's pretty. I can't even see it.
Did you go to HEB?
I did.
Dude, I'm going today. I'm so excited.
Oh, we had a dinner there last night to show off.